chat. Hello, everybody. I've just hit record. Thank you, Kevin and Maximilian. How is everyone doing today? Only 6 people here. Where is everyone? Are they doing the exam? Have they given up? What's going on? Anyway, we have quality here today, not quantity. So look, let's make the best of it, and I'm sure we'll have a good time. So in today's tutorial, it's a deeper understanding type tutorial. So I thought we could go through some of the harder questions. So everybody can talk, everybody can put their microphones on, do whatever they want to do. So let's talk through a few of these examples, and we can do some of the harder examples. And if there's anything you want me to talk about in particular, then just let me know. Okay, so all right, so let's have a look at the first question. So this is probably the first H question, right? So find a function f that satisfies this integral equation, okay? So integral equations are like differential equations. You're looking for a solution, and the solution is a function in this case. So let's work through it and see what they mean. Can anyone suggest how we might start the solution to this problem? Any ideas? Let me know on the chat, or let me know on the microphone. What do you think? If you were given this problem, how might you do it? Or have you already completed it? And what did you do? Let me know. Let me know. Any ideas? Any suggestions? Come on, don't be shy. There's only 7 people here and a dog, right? So that's maybe 7.5. Right? Who can suggest something? What might a strategy be here for this problem? Any ideas? Okay, so we've got this information. What can we do with this information? Come on, there's 7 people here. Let's get some suggestions going, people. What do you think? I'm not going on until there's at least 1 suggestion. Okay. Ooh, Oliver. First fundamental theorem. So first fundamental theorem says that we can differentiate these integrals, right? So let's try that, Oliver. Let's try your suggestion. See if it makes any sense. Okay. All right, so this is question 6. I might just turn that down a bit. Yep. Okay, so consider the following integral equation. So f of t is the unknown function. We want to solve it, solve the equation for f of t. Okay, and what we can start doing is differentiate this both sides of the equation, right? So differentiate both sides with respect to x. Okay, WRT with respect to. Okay, so if I differentiate this, right, when I differentiate this, it's going to disappear and the x will go here and the x will go here. And I can differentiate this. Now, what should I do with this? I'm going to change the order so it's nice. Okay, so if we apply, as Oliver's saying, the first fundamental theorem of calculus, we simplify that, and obviously that's just one. By the fundamental theorem of calculus, the first one, we obtain the following. Well, these things disappear and the x goes in here. So that's going to become x f of x. This one, it'll be negative x squared plus 1 f of x. And this will become 1. So we've got rid of the integral signs. All we need to do now is rearrange to make f of x the subject. So let's take that over there and we can factorize. And so let's divide by this on both sides. Bop, 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 bop. Bump, bump, bump. That's the solution. Okay, that is the solution. So Oliver was good in his suggestion there because he said, all right, well, these are like integrals with variables in the sign. We know we can differentiate them, so let's differentiate them and see what we have. Okay, so are there any questions for that particular example? Let me know either on your microphone or on the chat. Let me put a little poll in. Hang on, just doing something. There. Let me know what you think about lab test 2. Yeah, Kevin, it's a good question. Do we have to input the limits when differentiating the integral? Yes. Well, the top one you do, right? So this has gone in there, not 0 because it's a constant. Okay. So yes, we do have to input the limits, but only the variable parts. Okay, Kevin? You don't have to put in the constant parts. Does that make sense? Cool. Okay, so 2 people think lab test 2 was great. 2 people think it's okay. Who hasn't responded? Let me have a look. Brendan, what did you think? Are you there, Brendan? Hello, Brendan. You can see who's responded and who hasn't. All right, let's head back. I'll keep the poll open just for Brendan. See if he responds. Okay, so let's look at another question. Okay, question 8 is an interesting question. Suppose you have a continuous and increasing function on a closed interval. If we define these things this way, then explain why the integral of the inverse is equal to this. Okay, and use this to find the integral of this inverse. So this is a difficult question if you don't know where to start. Okay, and I think there's a hint in the course pack saying to draw a picture. Okay, so that's what I'm going to do. I'm going to draw a picture. Okay, just going to get my notes. Okay, so this is question 8. All right. Okay, so let's go back to my document camera and then we can see how we do it. All right. So they ask you to, I guess they're really asking you to draw a picture here. So what I'm going to do, I'm going to just draw an arbitrary increasing function. Okay, so that's going to be my f. And I'm going to look at a point on the x-axis and another point to the right on the x-axis, right? And they define these points, the corresponding y points, C and D, in the following way. Okay? And what we're asked to do is to explain. Okay. All right, I'm back. Okay, so the integral of this inverse is the following: b times d minus a times c minus the following integral. Okay, that's what we're really asked to do here. Okay. All right, so this is not an easy question. Okay, but we can, if from the picture, we can kind of work out these things in terms of area. Okay, so let's have a look. I'm just going to color in, let's say this is like area 1 or region 1. And this is going to be area 2 or region 2. Okay. Now, that area is the area under the curve and above the axis, right? So this thing will give you the area of A1. Okay. What do you think this integral will give you the area of? Who can tell me on the chat? What do you, which region do you think this integral will give you from the picture? What region? A2, Kevin, on point as usual. So this integral will give you, the area of this region. Okay. All right. Now let's look at what we've got left over. We've got this. What is B times D? Well, B times D, that's a rectangle. And what is A times C? A times C is another rectangle. So you can see, hopefully, that area plus that area is the same as that area minus that area. Okay? So that's all the question is really asking you to to do. So from the graph, A1 is this, or the area of A1, I guess. A2 is this. Right? And this bit here is just the area of the larger rectangle minus the area of the smaller rectangle. Okay? Hence, star holds. Okay, so that was not a complicated argument, but it helped to draw a picture and to look at these integrals as area. Okay, so once you know what to do, it's pretty easy. But you know, there'll be some people, how do I integrate this? How do I integrate this? You can't. You don't know what f is. Okay. So, are there any questions? Any questions? Would you like me to rewind it back and talk about some extra part or some element or something like that? What do you think? What I'm going to do is I'm going to make everybody a presenter. In case people want to say something or show something. Yeah, Kevin, it's a good question. Let's have a look. So Kevin's question is, for the integral of the inverse, wouldn't the curve be slightly different? Right? Well, no, not, yeah, not, yes. If you're looking at it on the x-axis, yes, but we're integrating on the y-axis here, Kevin. So it's a very good question, but we're integrating on the y-axis, which is kind of cute, right? Well, I mean, I think we're not really proving I-Chen, we're explaining. Okay, so the question, it's a good question from you. The original question says to explain why. It doesn't actually ask you to prove it. It asks you to explain why, okay? And then use this to find this thing, okay? So this is just a special case. So let's have a look at that, and we can do the second part. So the second part is like a special case of this, right? So this is it basically. This is one I've done earlier. So sine inverse would be f inverse. C would be 1/2. D would be 1. Okay. A would be pi on 6 and B would be pi on 2. Okay. So all I've done to get those two is taken the sine inverse of 1/2, sine of 1/2 and sine of 1. I've gone from this and applied the sines to get there. Okay. All right. So sine inverse of that is that. Sine inverse of that is that. Okay. So it's easy to integrate sine, not so easy to integrate sine inverse. So let's do that. You can, work this out to get this, and you can integrate sine to get that, and so you'll get that. So this is a particular example showing you that, well, this is an interesting thing to know, because this could be really difficult But this could be really easy. Okay, so this is an easy calculation over here, and I think that's what they're trying to tell you in this question. Okay. So what do people think? Pretty cool, huh? Pretty cool. So if you have the right kind of function like this, it's easy to compute the integral of the inverse on some interval just by doing this. Sweet. Sweet. Yeah, I like it. Awesome. Okay, so let's have a look at another one. Question 9. That's also a H question. So let's go over here. I'll kill that. All right, question 9. Suppose you have two functions, and basically capital U is an antiderivative or a primitive of little u. You've got this expression for capital V, where a is a constant. What is the derivative? And hence show that. Okay. So what do you think? Oh no, Chen, for part B, for part B here, right up here, you don't randomly choose it. You take the inverse of 1 and the inverse of 1/2. Okay, that's where pi on 6 and pi on 2 come from. Okay, so we don't randomly choose that. Okay, so this is C, this is D. Yeah, that's fine. Okay, so moving on to number 9. So you got that. Let's go and differentiate that. So we're asked to differentiate it. So let's use the fundamental theorem of calculus, FTC. All right, so we've got 9. And yeah. So let me just make some notes and then I'll go to my document camera. Okay. So let me switch over. Right now, I'm going to use this as the lowercase letter, okay, mu instead of u, because it's hard. These things get confused sometimes. All right. So for part A, well, let's use the FTC, fundamental theorem of calculus. Then the derivative. Well, it's the derivative of this plus the derivative of this. Okay. So for the first one, we can use the product rule. For the second one, we can use the fundamental theorem of calculus. Okay, so let's differentiate that, and we'll hopefully get a simple expression. Okay, so that's the first part minus that part plus, okay, so these things disappear and the x goes in there. Okay, so you can see that and that are going to cancel. And now it's just a matter of simplifying this. Well, big U dash is this function here. Okay. And that's the best you can do. That's the simplest form, I think, for the derivative. Now for part B, they ask you to do something else. Let me just have a quick look at that. Hence show that this definite integral, it can be written like this. Okay. So hence they want us to use the thing that we computed in part A. So let's try to do that. All right, so for part B, let's have a look now. Yeah, so if we just put in x equals a in here, that will become a, that will become a, and this will become 0. Okay. Right? Now, what else can we do here? Just check my notes. Now, also, we can integrate this. Okay, so this is also from part A. We just integrate both sides from x equals 0 to x equals a. Okay, so the fundamental theorem of calculus, the second one says, well, we can simplify this. We don't know what this is, but that's okay. Okay, and now let's go back over here. What is v of a? Well, we've got it up there. What is v of 0? Well, that'll disappear, and you'll get a times big U of x. Okay. So v of a is here from this original definition. V of 0, well, that will be 0. That will be 0. And that will be 0, right? Yep. So that's the left-hand side. And it's just the right-hand side over here. So we just rearrange that. And that's it. So bring that to the other side. Da, 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 da. Hooray! We did it. Okay, so that again, that's a reasonably difficult one because it's not clear how you do it. Okay, but again, going back to Oliver's suggestion at the start, you can just differentiate and then use your original definition to get some simplification over here, right? Okay. So any questions for that one? Any questions for that one? Let me know in the chat or turn your microphones on, people. Okay. So I'm just going to load up Maple in the background because there's something I want to show you for the next question. So just give me a minute and I'm just going to update my Maple, and there's something I want to show you. Okay, I can go over to the PDF now. Oops. So let me just go back to this one. So I thought we could do question 10 together, and I'm going to do it using Maple. Okay. So let me just open my Maple file and we can discuss that together. Okay, all right. Okay, so this function here, it's known as the floor function, okay? And it's a discontinuous function. And the idea is that it's the greatest integer less than or equal to t, right? So if you took the floor of 1/2, you would, the value of the floor function for t equals 1/2 would be 1, okay? So let me show you a picture and I'll put it together. Here they've just defined this integral and the function big F of x as the integral of the floor function from 0 to x. Use a graph to sketch these things in the interval. Is the function big F continuous and differentiable? Okay, so this is not an easy question, and I'm just going to do it using Maple. Okay, so this is one of the good things about having access to Maple. Okay, so what does this function look like as a graph? Is it continuous? And is it differentiable? Okay, so let's go off to my Maple window. Okay, so what is the Maple command for the floor function? Well, it's just floor, which sounds good. And here I've just got Maple to plot a graph of the floor function. It kind of looks like steps, doesn't it? Okay. So you can see here, let's just, I might just go in there and I might just plot, I don't know, t equals -1 to 3. Okay. So you can see here, as soon as we get to 0, it jumps up. And then it goes along here. As soon as it gets to 1, it jumps up. As soon as it gets to 2, it jumps up to 2, right? So that's kind of the idea here. Okay. So in the next line, I've just defined an integral of f with respect to t, and they get this function here. Now, you don't need that to answer the question, but I just think it's interesting to see. Okay. Now, I've made a couple of assumptions on x and t. I've put in the assumption that x is between -1 and 3 and that t is between 0 and x, okay? All right, so now you can check this out. Well, actually, let's look at the picture first. this is this g function from -1 to 3. So you can see, well, if I'm integrating that, I can sort of see some of the areas between the horizontal axis and the curve. But this is the really important thing here. Now I'm defining the function capital F to be the integral of the floor function between 0 and x. Okay? And what do these little tildes mean? They just mean there's a condition. There's some sort of restriction on the x values and the t values. Okay? So what I've done then is I've said, okay, well, that's good. I'm defining big F to be this integral. Maple can't calculate it, but what it can do, it can plot it. Okay? So this is the plot of the function big F for x between -1 and +3. So who can tell me in the chat, is the function a continuous function between x equals -1 and x equals +3? Who can tell me? There's 6 people here. Who can tell me? Is it continuous? Eloisa says yes. Ai-Chen says yes. Brendan, hello. It says yes. Brendan, you say yes also. Well, it's definitely a continuous function, right? I can go doot, 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 doot without lifting my pen or pencil off the page, right? Or off the screen. So it's definitely continuous. Oliver thinks so as well. The next question is this function differentiable? Is it differentiable at all the points between x equals 1, a -1, and x equals +3? Okay. Ai-Chen says no. Can you give me some points where it's not differentiable, Ai-Chen? Yeah. Yeah, you're absolutely right. Oops, you're absolutely right. It's not differentiable everywhere. I'm just doing something with my dog. Just wait. Okay. Now, yes, you're absolutely right. So there's a problem at these corner points, okay? And at the end points as well, right? So why doesn't this break the fundamental theorem of calculus? Why isn't this function differentiable? Why can't I differentiate this function? That's a big question for a Thursday afternoon or Thursday morning. That's a big question. Why can't I differentiate this function? Why doesn't it break the fundamental theorem of calculus? Can anyone tell me? Why doesn't it break the fundamental theorem of calculus? It's a good question. What do you think? Okay. Why can't I differentiate this? It's clear that I can't do that because of the corners, but doesn't the fundamental theorem of calculus say that I can differentiate this? What do people think? I mean, this is a deeper understanding tutorial, so I would expect more from people here, right? Why can't I differentiate this function everywhere? What do you think? Why doesn't it break the fundamental theorem of calculus? Who can tell me? Anybody want to have a guess? You know, usually you just You just differentiate this, and you differentiate this, and you replace t with x, and that's it. But I don't think you can do it with this one. So what's the problem? Maybe it'll help if I go back to the original graph. What's the problem? Yeah, it's not. It's an interesting one. It is differentiable at some points, but not at all points. Okay. So I'll give you a clue. It's got to do with little f. What do you notice about little f? What does its graph look like? Any ideas? Keep thinking. What I'll do is I'll bring up the fundamental theorem of calculus in my notes here. So here it is. So let me just see what it is. Aha. All right. So I'm going back over to, yeah, Louisa, it's an interesting idea. Let's have a look at PDF. So here's the first fundamental theorem of calculus. Okay, so what are the assumptions? If f is a continuous function defined on a closed interval, then this thing is continuous and differentiable. Okay, but the example that we just looked at is not differentiable. So what's the problem? Why can't we apply the first fundamental theorem of calculus to that floor function? Any ideas? Why can't we do it? What are people thinking? What is the problem there? Because it isn't differentiable. What's not differentiable, Oliver? I mean, we know that, but like we know that the f is not differentiable. But why doesn't the floor function satisfy this thing? Feel free to turn your microphone on if you want to have a chat. Any ideas, people? Why can't we use the first fundamental theorem of calculus? Yeah, but the yes, Chen, that's true, but like that's true. The conclusion doesn't hold, but what about the conditions of the theorem? Do the conditions of the theorem hold? Think about the conditions. What are the assumptions of the theorem? Okay, what are the oh, Eloisa, that's interesting. It's not about this interval. That's a good thing. It's about something else. You're getting close, Eloisa. You're getting close. So it's not about that, it's about something else. What's another assumption in our theorem? It's right in front of you. I'm surprised people haven't seen it yet. There's only two assumptions for this theorem, right? Oh, Aichen, now you're thinking. Ba, 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 ba. Let's look at the floor function. Is, is the floor function continuous? The floor function is not continuous. You've got these jumps. Okay? So the floor function is not continuous. This function here is not a continuous function. So it doesn't satisfy the conditions of the first fundamental theorem of calculus. Okay? All right. So that's the first really, I think, a really interesting question there. Okay. I think it's pretty interesting, but you never know, right? Like sometimes other people don't find it so interesting. No. Okay. So that's the first part. Kevin, because it's got jumps in it. Yeah, I know it is a jump. It looks bad in the maple plot. So maybe the maple plot isn't the best thing. So, but yeah, I mean, you can't have a vertical function, right? So even if I go back here and I go, well, you know, what's going on here? Well, that's just a maple error, but you can't have a vertical line there. Do you know what I mean? So I reckon it's pretty interesting, but not everybody finds it interesting, right? You know, not everybody finds it interesting. So what can I say? Yeah. I know it's a bit dumb, isn't it, I-Chen? The maple drawing isn't really good for this one, but anyway. All right. Okay. All right. So let's look at the next question. Next question is kind of down here anyway. So the question here is what's the question? Let me go back. This is question. Oh, got to go back. Just go back to the question. Okay. Yeah. Okay. Suppose you've got a function defined like that. Sketch the graph of the function and use the sketch to think about this function defined by an integral and indicate where capital F has maxima and minima. Okay. So if I go back then to this, it's easy to do in Maple. Here's my function. I've plotted it, blah, 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 blah. Think about the integral as area under a curve. So where this touches the axis, that's where the integral function will have a maximum. Okay, and then the integral function will decrease. It'll have a minimum here because that's negative area, that's positive area, and then it'll start increasing again. So you can see what I've done. I've just plotted it basically. So maximum, minimum. Okay, so those 2 points correspond to that point and that point. So that point is there, that point is there. Okay? So Maple's great for this sort of stuff. How good is Maple? Okay, so I really rate it. So again, you're just using the plot command and the integrate command, which is great. Now, what is this? Well, this is just a Maple's way of saying, well, I can kind of integrate this, but it's got a special name called a Fresnel integral. You don't need to worry about that. Okay. Well, all right, folks. I think that was a great tutorial, even though we only have 6 people here and a dog. But thank you for coming. And I've got to go now, but I do have another tutorial at 4 p.m. Sydney time today. So if you want to come along, come along. If not, I will see you tomorrow for the calculus lecture tomorrow. So I hope to see you then. Thank you for coming. And yeah, great to see you again, everyone. And yeah, if you haven't done class test 2, I hope you can do it soon. And I hope it was a big success. All right, folks. Bye.